We've got 23. Close enough. I was thinking today, there's just sort of one more topic that I would like to sort of cover with you guys. And then I was thinking we could spend like the second half of this time opening up for questions about the homework. How many of you guys have started the homework? Have questions? Does that seem like a reasonable thing to do?
Yes.
Okay. So go ahead and let me see. How can I do this? Put this here. I'll put this over here. If you do have homework questions, go ahead and use the raise your hand feature. And I'll be able, then I'll unmute you and you can ask your questions out loud instead of trying to type them into the guest chat. Okay, so really the only thing I want to cover today is a real short thing called the Rayleigh quotient. And the Rayleigh quotient is, it seems like a really kind of silly thing to do, just kind of idly sort of playing around with equations, but it ends up showing something pretty interesting that we have sort of seen incidentally as we've gone through and done a lot of these problems. Okay, so remember this applies to any boundary value problem that we're solving by transforms, because all such problems can be put into Sturm-Liouville form. So, you know, here is the, oops, let me make that yellow. Here is the Sturm-Liouville eigenvalue problem, right? So this is LU written in Sturm-Liouville form right here. Okay, the operator in Sturm-Liouville form, 1 over W times the derivative of P times phi x plus Q times phi equals negative lambda phi. Sorry, that should be L phi. Okay, and what we're going to do is we're going to take this equation, and it seems like a silly thing to do. We're going to assume that phi is an eigenfunction with associated eigenvalue lambda, all right? And what we're going to do is we're going to take this equation. It is the eigenvalue, eigenvector, is the equation for the eigenfunctions, and we're going to project both sides of that equation onto one of the eigenfunctions itself, all right? And so, you know, that involves taking the weighted inner product of both sides with phi divided by the weighted inner product of phi with itself. And so that's what I've done here. I have just, here is my operator acting on phi times phi times w dx. That's the weighted inner product of the left-hand side with phi. All right, and then I have the weighted inner product of the right-hand side with phi. Lambda is just a constant, so I pull it out of the integral. It's the integral of minus lambda phi times w dx. Okay, and then I divide both sides by the weighted inner product of phi with itself. Now, you see some cancellations emerge. In particular, when I project phi onto itself, I just get 1, right? And that makes some sense. How many phi's do I need? What you're basically asking is how many phi's do I need in the eigenfunction expansion of phi? Well, if phi is itself an eigenfunction, then the answer is most naturally 1. You need 1 of phi to create phi. And so you can cancel these two integrals, okay, because they're exactly the same thing. Then I can integrate by parts this thing, all right? What does that look like if I integrate it by parts once? Well, it's going to be, I'll have the integral of this. Oh, I've rewritten it here, right? So here I've just rewritten that left-hand side, this little piece right here. Okay, it's 1 over W P phi x times phi times W. The W's cancel, And then when I integrate by parts, I'm going to let this be the thing I integrate and this be the thing I differentiate. And when I integrate by parts, first I integrate this and I get p phi x times phi, and then minus the integral of p phi x times phi x. Okay, so that's another manipulation that I can do. And again, so far, this seems like we're just playing around with equations, for no specific purpose. But here's where things get interesting, okay? If we have converted this first half of the integral over here using integration by parts, we leave the second half alone. On the right-hand side, all we now have is lambda. Let's just multiply both sides by -1, in effect solving for lambda. All right, so we'll have lambda equals negative everything over here on the left, okay? And what do we have over here on the left? Well, we have these boundary terms, okay? And they pick up a minus sign because we multiplied both sides by -1. So that's what we've got here, negative p times phi x evaluated at the boundaries. Then I have this integral here. Okay, and when I have the negative sign, I pick up, it becomes a positive sign, integral over the domain of p times phi x quantity squared, dx. And then finally, I have this piece here that I never did anything with, and it picks up a minus sign, integral from a to b of q times phi squared times w dx. And then finally, I have this denominator here of the integral of phi times w. And this is an interesting statement for one and only one reason, okay? It still looks like a completely artificial, manufactured manipulation of equations, except that in physical problems, I should say in most physical problems, so that is most differential equations that arise from trying to understand nature. P of x is positive everywhere. And Q of x is less than or equal to 0. Okay. If we further assume that we have either Dirichlet or Neumann conditions, what have we just shown? I should say homogeneous. Dirichlet or Neumann conditions. P is positive, Q is negative. Let me even color code those. P is positive, Q is negative, and we have homogeneous. Yes, Jordan, that is correct. We have shown that the eigenvalues are positive. All right, so you probably have noticed as we've gone through these problems, we have never found any negative eigenvalues, right? And that is not a coincidence. It turns out that you can prove, in fact, we've just done it. We've just proved that if P of x is positive, and for instance, it's often like in our first unit, it was just 1. All right. So if our original operator here was phi xx, that's equal to P being 1, and 1 is positive, right? So if P is positive and Q is negative or 0, then there are no negative eigenvalues. If you have homogeneous boundary conditions, then these terms go away. If you have like a homogeneous Dirichlet condition on one side, then phi is 0 on that side. If you have a homogeneous Neumann condition on one side, then phi x is 0 on that side. And even if you have the more exotic, like mixed type boundary conditions, those, again, in physical problems, those are usually set up such that both of the terms that come from this will be positive, and furthermore contributing to the positive value of lambda. Okay, so this term looks negative, but usually it's 0, or in fact, there's a minus sign in here that turns that negative into a positive. All right, and so this is great. This basically confirms to us that we don't need to look for negative eigenvalues. Okay, and so, in the past, I've said, oh, well, really, you should look, but I'm not going to. Part of the reason for that is that, I had this result known to me in the back of my mind. And the great news now that we've covered it is that you can skip that step, with a clean conscience and not fear that you've missed something. All right. I should comment briefly on the possibility of lambda equals 0. All right. If Q is negative everywhere, then there can be no 0 eigenvalues. Because this integral here will be positive if Q is negative. If Q is negative, this term will be strictly positive. There's no way to make this 0 if phi is a non-zero eigenfunction. All right, so phi squared will be positive, Q will be negative, and you'll have this minus sign. And so this will be strictly positive, and you will have no 0 eigenvalues. But we did see 0 eigenvalues occasionally in some of our problems. And that can happen if Q equals 0. All right. So if P is positive and Q is 0, then the eigenfunction that we've most typically associated with a 0 eigenvalue is a constant, right? 1. And so this phi x term could be 0 if phi is a constant. And so that is consistent with a 0 eigenvalue out here if Q also happens to be 0. All right. So you do have to check for a 0 eigenvalue, but this tells us that you only have to do that check if Q is 0. All right. So if you're going through and you're looking for eigenfunctions, and I've given you a problem where Q is not 0, where Q is negative, you can skip both of those checks, right? You can skip checking for solvability because Q is not 0, and you can skip checking for negative eigenvalues because of the Rayleigh quotient, because P is positive and Q is negative. So although it seems a little bit strange and idle, like why would I do these particular manipulations, it really is pretty valuable and can further save you some time. In the same way that showing that something is self-adjoint is really valuable because it saves some time, understanding this thing called the Rayleigh quotient can save you a lot of time. The other thing I'll say is that just because Q equals 0 and a constant phi would correspond to a 0 eigenvalue does not mean necessarily that 0 is an eigenvalue. This is like an if statement, okay? If phi is an eigenfunction, then this statement is true, okay? But it does not work the other way. It's not an if and only if condition. It's just an if condition. So just because this statement might be true for an eigenfunction of phi equals a constant and lambda equals 0 does not mean that phi necessarily is an eigenfunction, that a constant necessarily is an eigenfunction. You still have to check, all right? This just precludes the possibility it precludes the possibility of negative eigenvalues. All right, that's really it. That's not very long, but it's really kind of the last topic in Unit 3. On Monday, we'll start PDEs. We'll start with the diffusion equation, and then we'll move on to the wave equation the week following that. This would be about the time that we have a test, like in the next week or two. I'll be real honest, I have no idea what that would look like. in this class. I know that the university is debating some changes to like the way we assign grades this semester. Have any of your other faculty like said anything about tests, what they're doing? Anything?
One of my classes is doing a take-home test.
A take-home test? Okay.
Yeah, some of mine has switched to like projects, like more like real world application stuff, and then like kind of like doing it take home. I kind of guess what Tinker said, and then turning it in.
Okay.
One of my professors used ProctorU, and that was not
Used what?
ProctorU.
What's that?
Basically, it's an online proctoring service. Like you have to allow it to use your webcam. And
Really?
like basically you have
Like, shine your
live proctor.
webcam at your work
view.
or something, your environment, and somebody just stares at you while you take your test.
Yeah, I wasn't a huge fan. Um,
Okay.
I've also taken tests through Lockdown browser.
Uh-huh.
I didn't have any issues with it, but I don't know if that's something you would want to do.
I have a professor that's just using a Canvas test, like as if it were a quiz.
Okay.
But I don't know how you do that in math, I guess.
Yeah, especially this kind of stuff. I will think about all those. I will also be carefully following I mean, they'll let us know if the department or the school decides to go to pass fail. They'll let us know pretty soon. And if they do that, then I'll probably just, if we go to pass fail, I'll probably just switch to homework only. Maybe assign a couple of extra problems here and there on the homeworks, and do a pass fail based on your homework grades. Okay, so I'll think about all that. Next, like I said, next week we'll do heat equation. The week after that we'll do wave equation, and I promise you guys it's going to be so easy because we've spent all this time on boundary value problems. We're going to get to the diffusion equation, the wave equation, and like actually solving them is going to be a piece of cake. What we'll spend most of our time doing instead is like interpreting the heat equation and the wave equation. Like we'll derive the heat equation and the wave equation. We will come up with general solutions to those equations. We'll talk about what they mean and what they tell us about heat conduction and wave propagation and that kind of stuff. But really, you know, the solution method is going to be exactly what we've done. Split the problem into boundary and interior, and then find the eigenfunctions, take the transform, and solve the problem. So it'll be very, very similar to what we're doing now. Okay. Okay. Nobody's a fan of ProctorU. All right. That is just I get it. Like, I think it's a really, on the surface, I think it's a really smart use of like the internet technology, but I just can't get past the creepiness factor of somebody just staring at you while you're taking an exam, like some anonymous person on the internet. So
I know the people that got accused of cheating just because they were looking down at their tests, because they literally watched like where you're looking.
Okay.
And if you're looking down at a test, like I said, I used it in high school, and people were accused of cheating because they were looking down at their test.
That's really strange.
It is also run by a bunch of college kids. Take that as you will, but it's kind of funny.
Okay. Really? Wow, that's fascinating. All right. You learn something new every day. So let's talk about the homework. What questions do you guys have on the homework? How can I help?
I have a question on the first problem.
Okay.
So I just wasn't sure how to do part E where you transform it. Yeah, if you could just help me get started on that problem.
Okay. Let me pull up a new page. Let me pull up the homework itself. Let's see. Homework 3. Oh, those are the solutions. And they're probably solutions to an old one. Homework 3 assignment. All right, first one, part E, transform the interior problem, finding the coefficients f sub n of the eigenfunction expansion for f of x. Okay. So by that point, you are going to have split the problem into parts, right? And you should have found ubxx minus 4 ub. What is q in this problem? And what is p? While I'm copying it down, think about that.
Were we supposed to convert this one to?
No, you don't. But I mean, you can convert any problem into Sturm-Liouville form. And since we just
Okay.
talked about the Rayleigh quotient, it's worth asking.
Okay.
Yes, Danny. Sturm-Liouville form is always just finding the weight function and then rearranging the operator accordingly. That works the same for the transform.
Sorry, that wasn't referring to Danny's comment. That was referring to the transform on number 1. Is the transform on number 1 and 3? If we know how to do one of them, we should be able to do the other one. Is that correct?
I mean, I would say yes, but I would say that about any problem. Like if you understand what a transform is, then taking the transform is the same on all problems.
But it doesn't change that it's interior versus.
Well, the
Oh, they're
interior
both
problem
interior,
is just
sorry.
the one left over with homogeneous boundary conditions.
Right.
So, yes. Okay, sorry. Here's your original problem. Not UB. Okay, I will just write. You'll have UB equals 0, and then you'll have UI XX minus 4 UI equals minus X. UI X of 0 equals 0, and UI X of 1 equals 0. Okay, so you'll have your boundary problem, you'll have your interior problem. Your interior problem has homogeneous boundary conditions. Just out of curiosity, you can rewrite. You don't have to solve this problem. It's sort of for no other purpose than identifying P and Q and connecting it to the Rayleigh quotient. This can be rewritten UX X minus 4 UI, right? In which case W is just 1, and P is just 1, and Q is negative 4. Okay, and so here's a case where P is positive throughout the domain, Q is negative throughout the domain, and so we're guaranteed to have only positive eigenvalues. And so that's a good thing to just have filed away. Can save us some time. All right, you should be able to find that the eigenvalues satisfy the eigenvalues and eigenfunctions satisfy this equation. And you should be able to explore, you get r squared plus lambda minus 4 equals 0. R equals plus or minus the square root of negative lambda minus 4. Okay, and so in principle, there are 3 cases, right? What are those 3 cases?
Greater than 4, less than 4, equals 4.
That's right. Okay, now you might be tempted to think, oh, but the Rayleigh quotient said there are no negative eigenvalues and no 0 eigenvalues, so we don't have to do these 2 cases. All right, what's wrong with that?
Dr. Norris, is it lambda less than 4?
Yeah, sorry. See, even I struggle to not just default to what we've done before. So what's wrong with this?
The less than 4 is still greater than 0, so you still have to check it.
That's right. The equals 4 is still greater than 0. And I guess you're right. In principle, there could be a couple of like 1 or 2 eigenvalues between 0 and 4. All right. Yeah, you're right. Okay, so we can do all 3. You should get for lambda equals 4, lambda greater than 4, what do you get?
Lambda greater than 4, I got lambda n equals 4 minus n pi squared.
Close.
4 plus n pi quantity squared.
Yeah, you lost a minus sign in there somewhere, or you
All right.
misplaced it when you were moving things around. So 4 plus n pi squared, and the eigenfunctions are cosine n pi x for this problem. All right, what about lambda equals 4? What do you get?
Lambda not equals 0, and phi not x equals 1.
I got
Okay.
lambda not as 1, I think.
Phi naught of x is
No, no,
1.
no. Wait, I got lambda not as 4, sorry.
Lambda naught is 4, right? That's the case. Lambda equals 4. And so it's lambda naught equals 4. Same, it's exactly the same thing that I just did over here is like, when we first did this, it was 0, and it's so tempting to just write 0, but really it's that dividing case, which is 4. And finally, if we check lambda less than 4, do we find any eigenfunctions or any eigenvalues?
No.
That's right. No. So we don't get anything. So we get, like 2 flavors of eigenfunction. What is the transform? And the transform you have to do kind of in 2 parts to reflect the fact that we have 2 families of eigenfunctions. One of those families is infinitely large in size, and one of them is just 1 unit large in size. But nevertheless, we have to do this. So for all of the n except 0, our transform is the integral of whatever the thing is times cosine n pi x dx divided by the integral of cosine squared n pi x dx. All right. But then that last one, that projection onto the eigenfunction phi equals 1, just has a different form. All right. And so these 2 statements represent our transform. The inverse transform is what? Suppose you have all these coefficients here. How do I get the original function back? Sum them, yes. So, so I have, I've got my standard n equals 1 to infinity of box sub n cosine n pi x. But I can't forget that last term. I have my 0th coefficient times my 0th eigenfunction, which is just 1. Okay, so I pick up that extra term there in the sum. So there it is. That's how we take the transform. That's how we take the inverse transform. Does that answer your question about how do I take the transform in problem 1?
Is box x in this case just x, right?
It can be any function, right? So we can take the transform of x. And when we do that, what we'll be doing is solving for the transform of u, right?
Yeah.
So let me start a new page here. When we take the transform, again, we have to do that in 2 parts. Right, here's our interior problem, the transform projection onto the cosine terms. What are we going to get when we take the transform of the left-hand side? Right, this is just LU. And what are we going to get? We take the transform of that. It's a Sturm-Liouville problem, so it's self-adjoint. What happens when we take the transform of a self-adjoint operator?
You just get u times, where is it?
Can you repeat the question again?
So I've got my problem, my interior problem. I've now found my eigenfunctions and my transform. And the next step is to take the transform of the interior problem. All right. And so I take the transform of the left-hand side and I set that equal to the transform of the right-hand side. What do I get when I take the transform of the left-hand side?
Is it negative ln n un?
That's right. All right. Every time I take the transform of a self-adjoint operator, I get minus the eigenvalue times the transform of the unknown itself. Okay, so yeah, that's right, Danny, as well. And that's going to give me minus x sub n here. What about the 0th term? Okay, so I have to do that separately. uixx minus 4ui 0 equals minus x 0. What do I get here?
Is it negative lambda not u naught?
It is negative lambda naught u naught equals negative x naught, where negative x naught is defined a little differently than negative x sub n. Chenyu, yes, I can show you the last page. Wait. I'm so confused. Oh, okay. I accidentally created a new page before the last page. Can I fix that? Yes, I can. Okay. So here's the last page. I split my problem. I looked at the eigenfunction problem. I considered 3 cases. I got some different eigenfunctions and different eigenvalues. And then I defined my transform and my inverse transform. Okay, now in the past, right, when we have done this, we've said, uh-oh, if lambda naught is 0, then this term disappears, and that causes us a problem. But do we have a problem here?
No, 'cause it's 4.
No, that's right, because it's 4. Okay, we call it lambda naught only because that's the most convenient number from like a counting perspective, right? If these are eigenvalues 1 through infinity, and then we have to add an extra one on at the front, it makes sense to call that 0 from like a computer science counting perspective, that if you're starting to count at a number before 1, you might as well call it 0. We could have called it, you know, lambda star or lambda special, and that might have cause a little bit less confusion, but it's not always true that lambda naught equals 0. And in this case, lambda naught equals 4. Okay, so all we have to do is solve these two algebraic equations and of course, calculate x sub n and x sub 0. All right, so let's do that. Let's start with the 0th one because that's the easiest one, right? That is going to be the integral from 0 to 1 of x times 1 dx, 1 times 1 dx, right? And so the denominator is just 1, and the numerator is going to be 1/2 x squared from 0 to 1, which is a half. Okay, what about x sub n? That is going to be 0 to 1 x times cosine n pi x dx over integral from 0 to 1 cosine squared n pi x dx, and I'll write that as n over d. We'll start with the denominator. How do I do integral of cosine squared?
Oh, 1/2 times 1 minus or plus? I don't remember off the top of my head.
Plus, right?
Plus.
So cosine squared
cosine.
becomes 1 plus cosine
Cosine
2 n pi x. If it had been sine squared, it would be 1/2 1 minus cosine 2 n pi x dx. And that's going to be 1/2 times x plus sine n pi x over n pi from 0 to 1. Sine of 0 is 0. Sine of n pi is 0. So there's no contributions from that term. And this is just going to be a half. All right, numerator. For my numerator, I'll use a parts chart. U to du, dv to v. The thing I'm going to be differentiating over and over again is x. And the thing I'm going to be integrating over and over again is cosine. Derivative of x is 1, derivative of 1 is 0. Integral of cosine is sine n pi x over n pi. Integral of sine is negative cosine n pi x over n pi quantity squared. And I've got this and plus minus plus. And so I get x sine of n pi x over n pi plus cosine n pi x over n pi quantity squared from 0 to 1. Sine of 0 is 0. Sine of n pi is 0, so no contributions from that term. Which gives me cosine n pi minus 1 over n pi quantity squared. So x sub n is numerator divided by denominator. I get 2 cosine n pi minus 2 over n pi quantity squared. What does that imply for un and u naught? Okay, so UN will be xn over lambda n, which is 2 cosine n pi minus 2 over n pi quantity squared divided by lambda n. And what was lambda n again?
4 plus n pi squared.
4 plus n pi quantity squared. U naught is going to be x sub 0 over lambda 0, which is 1/2 divided by 4. Okay, and there we go. So we didn't talk about solving for U boundary. I'll let you do that. But here's how we solve the interior problem.
Thank you.
No problem. Just trying to think if there's anything I can say to like illustrate big picture ideas here. We had our interior problem. We found the eigenvalues and eigenfunctions. Just like always, we've got sort of two sets. We've got an infinite set and a set with just one member. Since we have two sets, it means the transform has two parts. The inverse transform, of course, is just a sum of all the things, all the eigenvalues times the eigenfunctions. It might be worth pointing out that there's technically a 1 here, right? Projection constant times eigenfunction. Projection constant times eigenfunction, right? So there's nothing really special about this 0th term. It just has a slightly different form than the others, and so we have to treat it slightly differently. When I'm taking transforms of the problem, everything works the same for both sets. Again, the projections onto the cosines work just the tiniest bit differently than the projections onto the constant, but only because they're a different form. The basic idea is the same. We get the same type of equation as before. Because that lambda naught is not 0, this is not a problem. It's 4, so we can just proceed as we always do. The calculation of the projections of x also look a little bit different, but we go in the standard way for each one. We get two answers. We get two sets of values for the u sub n, and at the very end, we put them back together. Any other questions on this or other questions on the homework?
I'm having a bit of a trouble trying to understand what number 3 is asking.
Let's see, number 3. Okay. So in number 3, we're doing exactly the same thing that we just did for number 1, but with a different operator here. We're going to go through all the same steps since we have non-homogeneous boundary conditions. First, we're going to split the problem into boundary and interior components. And then we're going to look at the interior problem. And we need to put it in Sturm-Liouville form. This is actually already given to you in Sturm-Liouville form. So when you go to actually do solutions, this might be one thing that is a little bit confusing. This is already in Sturm-Liouville form. What is the weight function in this problem? That's right, 1 over r, right? Sturm-Liouville form has 1 over w times the derivative of p times the derivative of u. So in this case, p equals r, w equals 1 over r, and q equals 0. But when we want to actually solve things, Sturm-Liouville form is not that helpful. So we want to multiply that out. What is r times d by dr, r du dr? Well, that's r times, what's the derivative of this product? We get r, the second derivative, times the second derivative of u, plus 1 times the first derivative of u. Okay, and so that's just r squared urr plus r ur equals -1 is the standard form of the problem as written out in the homework. So, this is a Sturm-Liouville operator, and we'll split it into boundary and interior parts. We'll solve for the boundary solution. Then the interior problem will have homogeneous Dirichlet boundary conditions, and we'll find the eigenfunctions and eigenvalues associated with that interior problem, and we'll find the transform. Since this is a Sturm-Liouville problem, all those transforms and inner products will have a weight function of 1 over r in this case. And then we will obtain a transformed problem, which is again just going to be minus lambda sub n u sub n equals 1 sub n equals -1 sub n. And so we will calculate 1 sub n. We will solve for u sub n, and then we will take the inverse transform by summing up all the eigenfunctions.
I was having trouble solving for the eigenvalues and eigenfunctions on this problem.
In problem 3?
Yeah.
Okay. So the eigenfunctions and eigenvalues should satisfy r squared phi rr plus r phi r equals negative lambda phi. That's the operator. And then the boundary conditions are going to be homogeneous Dirichlet boundary conditions. Okay. So we can make that plus phi lambda phi equals 0.
I think your conditions are 1 and 2.
Yeah, you're right. You're right. Thank you. Okay, so this is very similar to the last example that we did in class, except we have a lambda instead of lambda -1. So this is not a constant coefficient problem. We spent so much time doing constant coefficient problems in ODEs that you might be tempted to think that the solution to every ordinary differential equation is to guess e to the rx. Okay, but that's only true of constant coefficient ODEs, which actually are a very tiny subset of all possible ODEs. And this is not one of them, right? This is an equidimensional equation. So equidimensional. It is the only other type of ODE that we know how to guess a solution to, and the solution that we guess is x to the p. X to some power, right? Because powers of x have the property that if you take two derivatives and then multiply by 2 powers, you get back a constant multiple of the original thing. And if we've got constant multiples of the same thing floating around here, we might be able to cancel and make them 0. So that's the reasoning that leads to that guess. Okay, so we plug that guess in. We get r squared. What's the second derivative of this guess? It's p times p minus 1. Sorry, r. And my children are screaming in the background. Okay, and then what do I get this term? I have plus r, p r to the p minus 1 plus lambda r to the p all equals 0. And we've got r squared times r to the p minus 2, r times r to the p minus 1, and r to the p. Those are all equal to r to the p. And so that gives us p squared minus p plus lambda r to the p equals 0. We can divide by r to the p because on the domain 1 to 2, it is never 0. So it's safe to divide by that. We get p squared plus lambda equals 0. All right, so p equals plus or minus the square root of negative lambda. There are 3 cases. Lambda greater than 0 is going to be the only one where we find any eigenfunctions in this case. Okay, so maybe what we're getting hung up on is that here we have p equals plus or minus I root lambda, because if lambda is positive, we can pull that minus sign out as an I, and we get phi equals r to the plus or minus I root lambda. And we know how to deal with exponentials. E to the plus or minus I something, we know that becomes sine and cosine. But what do we do with r to the plus or minus I root something? We play a trick. All right, e natural log of anything equals itself. So this is always valid. In this case, it also happens to be helpful because the natural log of something to a power, I can use my power rules to do that, to pull that power outside the natural log. And now I have, in fact, e to the plus or minus I something. Okay, and so that's going to give me C1 cosine of root lambda natural log of r plus C2 sine of root lambda natural log of r. Okay, I see that it's past 11 o'clock. So I'll let anyone who needs to go can go. I'm happy to stick around for a few extra minutes and continue answering this question, but I totally understand if you guys need to log out. From here, I just apply the boundary conditions, and they're homogeneous Dirichlet conditions for this problem. So I've got phi of 0, sine of 0, sorry, no, it's 1. Phi of 1 is natural log of 1 is 0 and sine of 0 is 0. So this term is not present. I get C1 times the cosine natural log of 1 is 0, cosine of 0 is 1. So I just get C1, not equal 0. Okay, that tells me what C1 is. Then I have phi of 2. All right, let me just go ahead and cross that out. So what is phi of 2? Well, it's C2 sine of root lambda natural log of 2, which also has to equal 0. I'd really rather not set C2 equal to 0 because then I'd have the trivial solution. Is there another way to make this true? Yes. If I let root lambda natural log of 2, that is the argument of the sine function, equal one of its roots. All right, so this means root lambda is n pi over natural log of 2, and lambda equals lambda sub n pi over natural log of 2 squared. And finally, my phi sub n of x. What happens when I plug root lambda back into my eigenfunction? I get sine n pi natural log of r over natural log of 2. All right, so it's a little bit weirder looking. We have the sine of the natural log, which is pretty weird, but everything has sort of checked out. we took the operator, we just said, how are the eigenfunctions defined? They're defined by setting L phi equals minus lambda phi, right? Always. That's always the definition of the eigenfunctions. L phi equals minus lambda phi. Well, I take the equation that I get, and it happens to be one of the two kinds that I can guess a solution to. It happens to be like the weirder one that's harder to remember. It's not as common, but nevertheless, I can guess a solution. I go through all the algebra, I guess a solution. I play a little trick here. I can turn that into sine and cosine of something involving a natural log, and then I can satisfy the boundary conditions just like I used to, and I end up with eigenvalues and eigenfunctions. The really important takeaway from this is that, again, and I'll say it, I'll keep saying it, I'll sound like a broken record, but that's okay. These problems are all structurally the same. The operators can be different, the boundary conditions can be different, but once you learn how to deal with like a sufficiently general problem, you treat every single one of them the same way. You can go back and do every problem we've done this entire semester using the exact same sort of set of steps. And if you can see that in your head, if you can see, this is the set of steps that I'm following every single time, the differences are just in the details. That's going to give you confidence when you do come across a new operator or a new boundary condition or something. You're like, oh, I've never seen this before, but I'm confident that I'm going to apply the same set of steps, even if as I do it, it seems unfamiliar. You should be able to proceed with confidence because you understand what the steps are and what they mean and why you're doing them.
Thank you.
Yep, no problem. Any other questions? How was your first week of online instruction? Was it awesome? Was it terrible?
Some of my professors have pretty bad internet connections, so.
Ah,